Hello, my name is George Meikle, and this is a tutorial on how to make this, which is a max external that does second order Markov chains, and it's made in RNBO and compiled using the source code that RNBO is able to produce. So, we're not going to look at how the whole patch works. I'm going to make this whole project available to download, including the external object. We're just going to be deleting this part and then building that up from scratch, primarily using Codebox inside RNBO to achieve this. So, if I just stop this, this is actually based on the second order Markov chain patch from the Algorithmic Composer website, which is included in the project, and there is a link to the tutorial here in the project, in the patch as well. So this website does show you how to do both first order and second order Markov chains. Second order Markov chains are generally more desirable for musical purposes because their results are said to be more self-similar than those of first order Markov chains. So for anybody who's not aware, Markov chains, the note or the number that is generated by a Markov chain is dependent upon the value of the number or the note that has come before it. In the source file, we're going to use a MIDI file in this example from the Algorithmic Composer website patch that is used to generate what is called a transition matrix. So first order Markov chains, the next note to be generated is only basically dependent upon the probability that the next note being generated is dependent upon the one note that has preceded that note in the kind of source information used to compile a transition matrix. So the results, whilst they're linked to the source material, they are somewhat more random in the way that they sound. Whereas a second order Markov chain is dependent upon the two preceding values or notes. The next note to be generated is dependent upon those values. And so the results, as I say, are characterized as being more self-similar to the original material. And so you get essentially like random, well, not random, but generative variations on the original material. So I can exemplify how this works and how a transition matrix is compiled just by using a MIDI file, which I have here, this patch. And this patch is dependent upon the call object, which does not exist in RNBO. So if we hit this, we come back in here, we can see this transition matrix. So what it's done is it's basically taken the stream of incoming notes in this MIDI file, and it's taken the first two notes, which are 54 and 57. These are MIDI note numbers. MIDI note numbers goes from 0 to 127. And they go from 54 to 57. And then within that MIDI file, the note 58 is preceded on two occasions by the two notes 54 and 57, and it works its way through the whole MIDI file. So you can see the first note, the third note essentially of this MIDI file is 58. It goes 54, 57, 58. So our next note pair is 57, 58, and that is followed on two occasions by the MIDI note 59. And then our next note pair is 58, 59, and that is followed by a 50 and a 58, and then we get a 59 and 50. That's followed by a 54, 50, 54 is only ever followed by a 62, so on and so forth. So the Algorithmic Composer patch is based upon using the call object to compile the transition matrix and to read the values from. Col does not exist inside Rainbow. So instead, we're going to do this using Codebox. And I will show you just how we're going to do that. So I'm going to get rid of this. We can actually have a quick listen to what this sounds like. So we should be able to hear the output of this. Now, because I'm coming out of my audio interface, I don't think we will actually hear the output of the note out object. So I will need to just load up like a synthesizer or something like that. We can do that in Ableton. And this isn't a particularly engaging MIDI file, it's just something that I did generate in Ableton. But if I just grab any old thing, like just a default operator patch, something like that, we take MIDI from Max 1, set that to in, we can hear that is generating this little melody for us. So yeah, as I say, the Col object doesn't exist in Rainbow, so we're going to have to do this via alternative means to create this, which is linked to Max's transport at the moment because I'm using the beep objects to sequence it. And as I say, we're not going to concern ourselves with the generation of notes or anything like that. This patch will be available for download. We're just going to concern ourselves with this object here. So what I'm going to do is I'm going to delete that, and we're going to create a new Rainbow object. I'm going to give it a title. I'm going to call it my Markov chain, and we'll do that, and we get this. So to begin with, we need a couple of inputs inside here. We can make this a bit bigger. Let's go like this. In fact, let's fill the whole screen pretty much with this. We need an in1, and we can give it a comment so that it's evident on the outside what is meant to be being received here. We'll call it list of values, and we'll do int. This is going to work with values of 0 to 127 integer values, and the list is going to have a maximum length of 128. So we've got our first inlet, and then we need a second inlet, which is just going to be in, and this is going to be an inlet used for getting the next note out. So we're just going to say bang for next note. Oh, we need a 2 there, so we've got 2 inlets. And then we're also going to need 2 outlets, which are to bang upon the completion of the transition matrix, and to output our note. So we want an output, we want new out 1, and we can give this a comment as well. So these comments show up on the Rainbow object in the parent max patch. We'll have a look at that in a second. We'll just call this like note/value output, and then we'll do another one. We'll call that out2. Actually, sorry, we want we'll leave it as, well, it's actually going to end up being our fourth output, so we'll call it out 4 for now, and Rainbow should automatically set it as the second, and we'll just do bang when transition matrix finished compiling. Have I spelled all that right? No. Compiling. Okay, can tighten that up a bit to something like that. Makes it a bit more usable. Okay, so we've got 2 inputs, 2 outputs. And first of all, this is going to receive a list input, but we want to make sure that we're not going to get anything, any lists longer than 128. So we're going to do list.slice. These list objects in Rainbow are just like the ZL objects in kind of standard max, 128. This will just slice out the first 128 values or less of any list it receives if the list is not 128 values long. And from this outlet it will output the rest if it exceeds 128 values. And then we need to, essentially, we're going to use, because it's standard MIDI range, we're going to use 0 to 127 for our range of values, but because we're going to base this around the use of data object, which is essentially like a buffer, we're actually going to increase everything by 1. So we are going to use a range of values inside Codebox and inside the data object, which is used to compile our transition matrix, of 1 to 128 rather than 0 to 127, because the 0 sample index values inside the data object are necessary for essentially calculating where we're going to store new values when we are compiling our transition matrix. Now, if we were in just standard max, we would be able to use, if I can open this up, we would be able to use just this vExpression object here, which, as you can see, adds 1 to every value. Now that, unfortunately, is not an option for us in Rainbow, so instead we're going to have to use list.stream with the value of 1. So we slice this list up that comes in into individual values. We add 1 to those values, and then we are going to put them back together into 3 integer lists, which will be used for our note pairs and the note that follows on from those note pairs for our second order Markov chain. I actually need a big trigger object, which we'll connect up later on, but it needs to be TLL000 BB, so triggering the list twice, and then 3 zeros and 2 bangs, although actually in the reverse order. The first one is going to be to reset our matrix. So that's going to be a send object, and we're just going to call that reset matrix, just like this. We'll actually make this way longer. And then over here, we'll focus on these two. First, we're actually going to take the length of the list, so we want list.len. And we are going to take 2 away. The reason we're going to take 2 away is because the first 2 notes are immediately put into a note pair, so of the incoming list. So they're not actually, essentially what we want here is the total number of notes that are assigned to a given note pair. Now, the first 2 notes are not preceded by another 2 notes. Obviously the second note is preceded by 1 note, but we need it to be preceded by 2 notes. So we can basically subtract 2 from our list length to get the number that we actually want, which is the number of individual notes that we're going to be storing in our transition matrix. So hopefully that makes sense. We're just going to do -2 here, and here we're going to do list.stream 1 to get our individual values. We will continue to stretch this out a bit to make room for everything, and then we're going to do clamp 0127 just to make sure that any values outside of that range are retained within the working range that we want. Then we're going to add 1 to that. Oh, wrong thing. Add 1. So we're shifting everything up to be in a range of 1 to 128. And then we're going to send that into a list.stream 3 to create our 3 integer lists. Now I could exemplify this, but there's quite a lot to get through in this tutorial. But essentially, if we passed a list of values into here, we would ultimately get out a load of 3 integer lists coming out of here, and then each of the integers would be 1 higher than the corresponding integer in the input list. Now we need another trigger down here. We need a TLB, so triggering a bang and then the list. And we actually need a counter. So we're going to do counter 126, which is the default for this counter, but we will override that. So this is to count how many values essentially pass through here and into Codebox for the generation of our transition matrix. And we are going to actually change the maximum value to the length of the list here. So we're going to use another trigger object here, which will be TBI, so triggering an integer followed by a bang. And what we will do is we will send, we'll make it so we can actually see that. We'll connect that up to there. So we're going to override the maximum count for the counter, and then we're going to send the bang here so that it resets the counter to 0 essentially immediately, and then it is ready for the processing of everything else. We also just want to see what comes out of this counter for reference, so we will stick that there, and we will leave that just about there. We're actually going to need to add something to this as well from over here, from our second bang, which I'll do in a second. But essentially we want our bang to go up into our counter that is used for counting the number of notes that passes through here, and we use the counter hit maximum flag here to actually release a single bang when the transition matrix is finished compiling, which will stick down here. So we'll connect all that up shortly. We've got our bang going to there. We can just align that like that, get that out of the way. And over here, what we actually want is we want another trigger. We want T31. Now what this is going to do is it's essentially going to clear the kind of cache of information inside our list.stream object in the same way that the ZL clear would, the ZL clear message would in standard Max. Now we can't have messages with words inside RNBO with symbols, so instead we're just going to use this. We're basically just going to resize this ZL stream, so we're going to change it from 1 and then back to 3 whenever we want it to be cleared, and we'll connect that up to our second bang. So when a list is received, it will first reset the matrix when we can connect up that reset matrix send object there. We'll reset the matrix, and then it will reset this ZL stream, because this basically every time a new single value is received, it will output the last 3. So we're always going to get like the last 3 values. We're not waiting for 3 and then another block of 3 and then another block of 3. We will get 3 and then the second 2 of that 3 followed by the new value. That will make us a new 3, and then the second 2 of that 3 and a new value, if you see what I mean. So it will retain whatever the last 3 values are that are stored in it. So we just want to clear that out, and we can do that here by resizing it, by changing it to a ZL stream 1 back to a ZL stream 3, and that will empty it out. And then this, where are we? The carry count. What we actually need to connect that to is going to be down here. Let's just move this out of the way a bit. Shift everything over and up to make some room. Just like that. We're actually going to take this counter hit maximum flag, and we are going to connect that up to a gate, which is going to be connected to here. So we want this to be gate 1 0, so that means by default it's definitely going to be closed. It should be anyway if we just call it gate without defining that we only want the 1 output. We want its default to be 0, but by doing this, we're just ensuring that that is definitely the case. We can visualize that just by connecting this to a toggle, so we can see what happens, and then we will get a 1 whenever this hits the maximum, and then it'll go back to 0 when we are not at the maximum, which is quite effective. So we will need to route that. Aligning it won't work in this instance. Just stick that down there, and then essentially this is going to take the current note that is being stored in the transition matrix. This is going to be connected up to an outlet of Codebox that gives us that information, but we actually only want it to bang, right? And you'll see how that connects up in a minute. So we're going to have TBI. The I can be connected to a number box, just so that we can see that the B, will be connected to there, and that bang will be passed through our gate only the final time. So we will just get 1 only when the final note has been stored in the transition matrix. So we will just get 1 bang from outlet 4 when the final note is stored, which is what we want. And then here for our note output, this is fairly straightforward. We basically just need to reset its range. We'll have a number box so we can see what's happening, and that will just be connected to a -1. So I'm kind of doing this all in reverse. These are some of like the last bits that we need to do, but you'll see how it connects up, and I will kind of review what's actually going on here in the rainbow patching outside of Codebox as well. So that gives us a place to start. So now we need to create a Codebox operator in the middle here, and I'm actually going to move some of this stuff down to get a bit more space, because we want the Codebox operator to be quite large, just so we can see a good deal of kind of what's going on in there at once. So here we're going to connect this up to Codebox, just like that, and we can resize that so that it is nice and large. Take our into, and we can connect that up to what we can do when we've created that, the necessary coding for that inlet, but we'll leave that there for now. Okay, so this is the basis of what we need to get this to work. We also need a data object, which we are going to call transmat for our transition matrix. So I'm going to make data transmat, and I'm going to give it a default sample size, sample size of 2. I'm going to give it 128 channels. Now this could be 126 because we're never going to get a list longer than 126 different note values, but we're just going to do 128 to be safe. Now, when I first, decided that this is the way I was going to do this and make this external, I was actually going to increment the channel count every time that I added a new note pair to the transition matrix. But unfortunately, that doesn't work, because if we have a look in here, whilst if we just make this one sample long and one channel big, whilst you can increase the sample count without clearing the contents of a data operator, once you increase the channel count or change the channel count, the contents of the data object are deleted. So if we write like 6 into sample 0, you can see here that we should get a 6. Now if we increase the sample count to 2, then we can write a 7 into sample 1 and we get a 6 and a 7. You can see the sample here, that's fine. We can increase the sample count again to 3 and we can give it an 8. No, we'll leave that 7, we'll give this an 8. So now we've got 6 in sample 0, 7 in sample 1, 8 in sample 2. There are 3 samples. However, if I increase the channel count to 2, we lose everything that is in there. So we need to essentially use a load of for loops within this predefined channel count to make this work, which is fine, but we're just giving the channel count that essentially, if there were no note pairs, there were no repetitions in the source material used for the transition matrix, then we could have up to 126 or maybe 128 different values inside that transition matrix. So we just want to have enough channels to accommodate all of that, even though we will never use in reality, in practice, anywhere near that channel count. If you just look here, when I hover over these, you can see the comments that I have for my different inlets and outlets on my rainbow object. So go back here. So we've got our transition matrix here, and we need a few other things to go with this. So we're going to change its size, which we can do with the size attribute. You can do it with samples, but we'll just do size as well, set size. And we are also going to have to be able to clear it. We want to just set clear there. So we'll have those two, and then these are actually going to be connected up to our reset matrix. So we're just going to change that to receive reset matrix. Pull that down there so it's slightly out of the way, and then we want TB2. So first of all, we're resetting its size so that it starts off as having 2 samples, which is enough to store a note pair and and the first note that follows it. Enough to start the first note pair and the third note in the incoming list, which is the first note that is preceded by that note pair in the incoming kind of information. And then we're just going to clear it out after that, just like that, and we'll leave that there. Okay, so now when we receive a note list, this transition matrix, this data object, whatever's stored in there, will be cleared out and the sample size will be reset to 2 samples. The channel count is left alone so that we never overwrite accidentally what is in there when we aren't wanting to. So inside Codebox now we need to create a few things. We're going to create some parameters and also a state operator which will reference our data object out here, the transmat data object. Now we need to make params and a state, because in Rainbow we can create variables, but variables are not stateful, which means everything inside that happens inside this Codebox object essentially is like one big one big function, and every time we make a call to that function, to what happens in the code box, all the variable values are essentially reset. They are not carried over. If we want something to carry over to the next call to code box, then we have to use the state operator to create a kind of stateful variable value. Sorry, not the state operator, we just have to use a state variable. And that's what we're going to use for our transmat. And params are very similar, but we can also kind of reset and set the value of params from outside the Codebox operator, and actually from outside RNBO maybe as well. If we expose those parameters to the outside. I don't think we're going to be doing that. I don't think that's necessary in this case, but it is possible, I believe, but we do need to control them from inside the RNBO patch to reset their value. So we're going to have 3 params which we can reset. We're going to have param, and then to define these we put at param, and then we put it in brackets, and then we need curly brackets as well, and we need a minimum value. We don't actually need minimums and maximums, but we're going to set them. So this is going to be 0 as our minimum value. Our maximum value is going to be 128. And we can close those curly braces and then close the braces, and we are going to give it a name of active chans, and we're going to give it a default value of 0, just like that. And this is used for counting the number of note pairs that are inputted into our transition matrix. The next parameter we want is going to be our note out parameter, which is basically going to be the note that we are outputting from our transition matrix when we're generating our second order Markov chain. So we're going to call that param again. This we don't need a minimum or maximum because that's kind of predefined by everything that goes on up here. It can only be between 1 and 128. We're going to have note out. We're going to set that to 0. And then finally we're going to have another param which is called last 2 notes, which is used to store the last 2 notes generated by the algorithm that is in here, and then recall those last 2 notes and compare them against all of the note pairs in the transition matrix in order to determine if there is a match, and therefore randomly select one of the notes that is preceded by that note pair in the original material that is used to compile the transition matrix. So we've got param min 0 max 128, and that is our active chans param with a default of 0. We've got our note out param again with a default of 0, and we've got our last 2 notes param again with a default of 0. And then down here we're going to have state transmat equals new data. So we're giving it the same name as our data object out here, but this isn't actually the name that is used to reference this data object. We actually use the name that we put in parentheses here. We do transmat as a string, and this will reference this as a data operator inside Codebox. So this data operator is referencing this data object, and the reference that we are giving to that, essentially the variable name, is just transmat as well. So it's the same, just for simplicity. So we are also going to create a number of set objects out here so that we can reset the value of all of these parameters. So we need to let's go on there, param note out. Oh, that's not an equals. There we go. So here we want set note out, and then we want set last 2 notes, and we want to set active chans, just like that. And then we'll connect all of these up here, just like that, drag them down, get them out of the way. We'll make a bit more space between this and that. Oh, this and that. Move this down as well. Oh, wrong thing. Just drag that out of the way. Give them a bit more room. And then these are basically going to be triggered by these. So our zeros from our trigger object. So when we input a new list, before that new list passes through into Codebox, we will reset the values of all of these parameters back to 0, because we've got our 3 zeros in our trigger object, so that we are at a point which we are ready to go. So that is about where we want to be. We can also add a third inlet here now as well. We'll call it in3, which is just a manual kind of reset. So we're just going to do a comment bang to reset. Yep. So we're going to connect that up with 2 zeros to, we don't want to reset the channel count here. This is because Markov chains can at times get stuck repeating the same note if the information in the transition matrix is conducive to that. If there's, say, like only one note followed by a certain note pair and it gets like preceded by a certain note pair and it gets stuck on that, then yeah, you can kind of get stuck in these perpetual loops or just on a single note. So we just want a button to be able to reset the generation. We are going to encode something in here to, I think, try and kind of mitigate that issue anyway, if I recall, but this is just a manual way of doing it regardless. So we just want to set note out and last 2 notes just like that. We'll actually switch that round to do it the other way. So we reset the note out first, and then the last 2 notes second, leaving the channel count unaffected. Okay, so we can just neaten that up a bit by aligning those, make that a bit neater. That's fine. Good. Okay, we can also we can drag this up a bit higher and then align all of those as well. Good. Okay. So next we need to create a function to encode the notes that are coming into our Codebox operator so that we can store them and recall them. Now, the original patch, the algorithmic composer patch, the max patch, uses a process of concatenation whereby you essentially squash the 2 notes together. And I've done this, but there is a bit of an issue, and the issue is that for what we want to achieve, it only really works with it only really works if you have you're working with integer values that are of the same number of digits. So if you're working with like a workable MIDI note number range, for instance, of say like 48 to 64, say that 1 octave, or 48 to 96, whatever it might be, as long as you're only ever going to be using integers that have 2 digits in them, this isn't a problem when you come to kind of separate them back out, but it becomes a problem when you are using, say, potentially you have a 1 which is preceded by a 127 and a 92. Then we get the kind of problem of figuring out, where the dividing line is in this singular number, which is these 2 numbers squashed together, not multiplied or added together or anything like that. We have this problem of figuring out where that dividing line is, and therefore it becomes difficult to separate out the numbers appropriately. If they're only ever kind of like 2-digit integers, it's easier to work with, because you are basically just doing a modulo 100, if I recall correctly. Anyway, I've set up an algorithm here to demonstrate this in Codebox, and another one because I was actually like decimalising the numbers, but that gave kind of round off errors when reverting back to the non-decimalised version of the numbers. So that wasn't viable either, and I'll just demonstrate this now. So this is just, we don't need to worry about what's actually going on here. This is just a concatenation algorithm that I got off the internet, which is fine. Yeah, if I basically just input a list, say like 11 and 12, here we get 11 and 12, and this is our second note, which is fine. We've got a function here to get the second note of this note pair, and that's perfectly fine. I could change this to like 11 and 97, and it would give us 97. If I could change this to like 33 and 97, that's not a problem. We're always getting our kind of second note. Whereas if I go 1, 2, 7, we're still getting 89, or we're still getting the number here. But let's try and do, say, like 6, and then say 111. See what happens. There, we're only getting an 11. And that's because we are doing the equivalent of a modulo 100 here using the wrap operator. We're wrapping these values between 0 and 100. So we're actually getting 11 because it can't exceed 100. So we would need to basically be able to dynamically alter this second value to be 1,000 for when we exceed 99, or when we exceed 100, sorry, either 99 or 100, so that we would get a 3-digit integer coming out here, and we'd need to change it to a 10 when all we want is a 1-digit integer coming out of here, I think. But anyway, it doesn't work for this reason. You can see that we should be getting 6, 1, 1, 1, 1. This split this up as 61, 11, not 6, 111. So we're not getting our last value out accurately. The other option was decimalising these, which is basically like dividing the second integer by 1,000 and then adding them together and then kind of multiplying that back out down here so that we get a floating point number. Say if we had 132, we'd get 100.032, I think. 32, yeah, 100.032. And out here, you can see that we actually have this round off error. When we're looking at it as a floating point, we get our 32, but when we're looking at it as an integer, we're getting it as a 31. And this is not an uncommon occurrence. Sometimes it's right, other times it is incorrect. You can see these inconsistencies coming out down here, 40 and 41. This is our integer value, this is our floating point value. So essentially when we're converting it back to being an integer, we're getting these round off errors. So this isn't appropriate either. So instead, the way that we're encoding these is using a process of bit shifting. That is essentially, if we just have a really quick look at this, if I write the number 1 in on this calculator, we have the big number here, which is our actual number, and then here we have our kind of like binary representation of this. If I have the 1, because we're using 128 values, if I just write in 128, you can see we're using the first 8 bits here to store 128. If I do, say, 129, we're still using the first 8 bits. I think up until 256 we're using the first 8 bits. If I do 255, yeah, 255 first 8 bits. If I do 256, we then go into the 9th bit. So what we're essentially going to be doing, because we're using the first 8 bits to store values of 1 to 128, we essentially are going to shift it to the left by 8 bits to give us a bigger number. And this gets rid of our issue with concatenation and with round off errors in order to give us an accurate way of encoding our note pairs and then decoding them when we potentially have a note pair. I'm calling them note pairs, but these don't have to be notes. You could use your MIDI range of 0 to 127 for kind of filter cutoff frequency or whatever you want, but I'm just going to continue to refer to them as note pairs for simplicity. Yeah, what am I saying? Essentially, by bit shifting it by 8 bits to the left, which is equivalent to multiplying it by 256, what should we do? 1, we've got these first 8 bits. If we just look at these first 8 bits, we've got 0, 0, 0, 0, 0, 0, 0, 1. If we multiply that by 256, we get the same thing, but in the second 8 bits. So we're now using up to 16 bits, right? And the same thing is the same as like shifting it to the left 8 times, right? So this way we never have to do a transition from an integer to a floating point value, as with the kind of decimalisation process that I've tried using, which can result in round off errors. And we also don't have the issue with separating out two concatenated integers. So yes, essentially the way that we make this this encoding function is, we'll do this down here, we go function, we'll call it encode, and this needs like 2 arguments, A and B, and then we're going to build our function down here, and we need a variable, so we'll do let encoded note pair. We're going to define this as an integer because we can define the type, the data type that we want our variables to be. We don't have to in all instances, but it's just, it's a surefire way of making sure that we're not having any kind of errors in there that we don't want. We're going to define this as an integer with this little colon here, and we're going to make that equal to, in brackets, we're going to do A, which is our first argument, bit shifted using this operator by 8 bits to the left, plus B. So that is the way in which we're going to encode our note pair. So we're going to bit shift our first note in our note pair by 8 bits to the left, and then we're just going to add the second value to that. And I will come back to how we're going to decode this later on when we get to that stage, but in this function we just want to do return encoded note pair. That's fine, and then we can close the curly braces on that, and we've got an encode function as an integer, which is great. So next, we need to create a function to compile our transition matrix. So here we're going to do another function, and we're going to call this compileMatrix. And this is going to take a list, obviously. It's going to be working with these 3 integer lists that are coming in here. And we're going to call this note list and define the fact that it is going to be a list in the same way as we defined our integer variable encoded note pair up here. And then we're going to open up this function and just put that there. So we need a few variables in here. First of all, we need a transition matrix size, which is like our sample size of our global transmat data object. So we're going to do let transmat size, which is going to be an integer, equal, and we're going to use the dim or dimension operator of transmat, which basically just returns the sample count of our transmat data object. We also need a number of channels, so we're going to do let transmat chans another integer equal, I want that to be chans, equal to channels, okay, so here we've used the channels method of this transmat data operator, which we have up here. So this is our sample size, which we can comment in here, sample size of transmat data operator, and here we have our chan count of transmat data operator. Now I'm not going to be as thoroughly commenting this out as I would be, or as I have done when I've made this in the first instance, just because it takes a lot of time. But I would encourage you to kind of comment out everything that I'm saying, if it makes any sense. If I'm doing any sort of good job of explaining it as I go along, yeah, comment it out yourself, just for reference. So next we need another variable which is going to be the current note. So we're going to call this let current note, again another integer, equal note list. This is our note list argument from our function up here, dot pop. So this is the third note, the last note of our 3-note note list, or value, as I say. This doesn't have to, they don't have to be MIDI notes. They're just values, they're just numbers in kind of MIDI range. They can be anything, but I'm just going to refer them to them as notes for simplicity. So last note of 3-note list, arriving at list in 1, which I don't think we've actually defined list in 1 yet, but we will do in time. Next we need let preceding 2 notes, another integer, equal, and then we're going to call our encode function. We're going to apply that to note list 0 and note list 1. So these are our first 2 note values from our 3-note note list that is entering Codebox from our list.stream3 here, and we're encoding them by calling our encode function inside our compileMatrix function here, to create a new integer made out of these first two notes of this 3-note note list. Okay, so what we want to do here as well is just make a kind of reference of what's going on in the Max console. We can do that by using post, and we'll say what have I called this? My Markov chain, my underscore Markov underscore chain, just so everything is tagged with that. I'll do preceding 2 notes, and in brackets we'll put encoded, because it's not actually going to have any relevance. I mean, it has relevance, but not on the face of it, because you know the first number is going to be multiplied by 256. It's not going to have any face value relevance to the notes that we're putting into it. So we'll make a note of the fact that these are encoded, and then we're going to put preceding 2 notes, and that will be posted to the Max console. So now what we want to do is iterate through all of the channels in the transmat data object in order to check the value of the first sample in each of them. Let's just check we've got no errors here. No, that's compiled fine. So I can write that in, iterate through samp 0 in, iterate through samp 0 of all chans in transmat data object. And here we want a for loop, so we want for we need something to count through our number of loops, so we're going to do let, this is declaring a variable for counting through, let chan, which is going to be an int equals 0, as long as chan is less than transmat chans, we're going to do chan plus plus. So if you recall, our transmat our transmat chans variable is our kind of is declared up here. So our transmat chans is equal to the number of channels in our transmat data object, which is essentially 128. Yeah. So as long as that is true, we're going to iterate the channel value, and then inside here we need another variable. So we're going to do let sample 0, which we want to be an integer, equal peak, and this is the peak operator to have a look at what is happening inside our data operator, which references our data object. Out here we're going to peak at transmat, we're going to peak at sample 0, and then we need to define the number of channels we have here by doing this, channels 1 to 8, and then we actually close this, these parentheses, and in square brackets we just put chan. So we're looking at, essentially what we're doing here is we're looking at, that's cleared the error. Essentially what we're doing here is we're looking at the value of sample 0 inside all of the chans, yeah, because this chan variable increments by 1 every time we loop round, so the channel count increments by 1 here, and the sample 0 variable has the value of the first sample in those channels assigned to it at each loop round. So we can then post that to the Max console just to see what's going on. So we're going to do post. I'm actually going to do this. This will make things a lot quicker. Let's just copy that, put not a lot quicker, but marginally quicker, and then we can just copy it from there every time. So post, we want this, and we want this to say sample 0 at channel chan equals wrong thing, equals sample 0. So we can just see what's going on as we're compiling this this transition matrix. Okay, so that is compiling it. Well, it's not actually. That's just looking through to see what the value is. We need to determine what happens if there is no value stored there, or if there's no match with our note pair, or if there is a match with our note pair. So essentially we do this with an if-else statement. So down here we're going to do if preceding two notes is equal to sample 0. So our preceding two notes variable here is our first two notes of our 3-note list that comes into our code box up here. If that is equal to, it's actually the encoded version of that, remember. So if that is equal to the value that is stored at sample 0, it means we have a note pair match, which means that that note pair has come up previously, and then we need to assign the current note that is preceded by our current preceding two notes value at an index, a sample index of the channel that we're currently in. Yeah, hopefully that's clear. So we've got if preceding two notes is equal to sample 0, we can close that and open up some more brackets. We are going to first of all, we're going to post, just for clarity, we'll take that, paste that in there, post, and we'll do matching pair found. So that's nice and clear. And then we will do another for loop inside here. Okay, so if preceding two notes is equal to sample 0, we will do another for loop, and we will do for, and this time we will do let sample, which will be an int, equal 1, because we can start counting from the second sample index, which will be sample index 1, because at sample index 0, the first sample index, we have our note pair stored, so we don't need to bother counting through that. Not that that saves much in terms of efficiency, but it's something. If it's let sample 0 equal to 1 as long as let sample equal to 1 as long as sample is less than transmat size, which we know up here is the current dimension of our transition matrix in terms of its sample size. We are going to increment the value of our sample variable, and then inside here we're going to do some more stuff. So we're going to do some more stuff. We're going to compare, essentially we're going to increase the sample count by 1 if necessary, but we're going to store the current note at a sample index. We may need to increase the sample count of the transmat data object in order to do that. And I'll explain this as clearly as I can as we go along. So here we're going to do let sample val, which we want an int, so this is another variable, equal to, and we're going to use the peak operator again, and we're going to do transmat, which is the name of our data operator. We're going to look at sample. We need to define the channel count again, so it's channels is 1 to 8, and then we can close that, and we're going to look at every sample in the current channel that we're in, and then we want actually another variable which is going to be our final sample value. So we're going to do let final sample val, another int, equal, and we can just copy that but change it slightly. So we'll do that, instead of having that as sample, we will do transmat size -1, because the first sample index is sample index 0, not sample index 1. So the actual transmat size, the number of that will be 1 greater than the sample index of the final sample in the data operator. So here we are peaking at the final sample value, so the value of the sample stored in the final sample index at the current channel of the data operator. We're assigning that to this final sample val. Okay, so here we need to do a couple of things. So this is where we make a decision. Are we going to increment the sample size, the actual dimension size of the data operator, or not? Essentially, if you imagine that you have, say, 2 note pairs currently stored in your transition matrix, the first note pair has 4 notes that are followed by that note pair. So that goes up to sample index 4. It's 5 samples long because the first sample index 0, is the note pair itself. And if the second channel contains a second note pair, but that only has 2 notes associated with that note pair, then we essentially have the note pair in sample index 0, the 2 notes in sample index 1 and 2, and then we have 2 0 values in sample index 3 and 4. So then when we get to sample index 3, which is a 0, we will store the next note associated with that second note pair that's stored in channel 2. We will store that in sample index 3. Now, if both of these channels, both of these note pairs had 4 notes associated with them, so they were both filled all of the 5 samples, with first of all the note pair and then the 4 kind of following notes that are preceded by that note pair, then we would need to increment the sample size by 1 in order to open up a new 0 value sample index, which will be at sample index 5, the 6th sample index, and then we would store the note, the current note that has matched with that note pair at that sample index. So that is what we're going to do here. So essentially, if the sample value, we need this to happen inside our for loop. So we're going to do if final sample val int we're going to do, just repeating the same thing again, we're going to do if sample val is equal to 0, then we're going to use the poke operator to write our current note to the corresponding channel, to the corresponding sample in the current channel. Yeah, so we're going to do poke, and we're going to do transmat, and we're going to do current note, because we want to assign our current note variable, which is the 3rd note in our incoming 3-note note list. We want to assign or write that current note value to a sample index on a given channel, and then we're going to use the current sample count of this for loop as our sample index and the current channel count of this for loop as our channel. So we're going to write, we're going to poke transmat with the current note value at sample index X and channel count Y, yeah, whatever X and Y may be in this instance of this iteration of the for loop. And then we can post that to the Max console so we can see what's going on. We will do like if we just post like where are we at? We'll do post, and then here we'll take this bit again. So we're going to be doing this a lot, and we'll do new sample val stored at channel chan index sample equals current note. So then we get that posted to the Max console and we can see what's going on, and then we're just going to break that for loop at that point. So that's what happens if we have an empty sample index. If we don't, then we need to do something else inside this for loop. So this needs to go here. For loop needs to go here. For loop. Getting confused by all of these brackets. So we've got our for loop, our if statement, our for loop, our Our if statement actually needs another bracket. Is that right? There we go. Okay. So else, actually we're going to do else if, because I did test this with not actually using this final sample val. And I think I occasionally had issues with it kind of like perpetually looping. So I'd create a new sample, it'd find that sample was 0, and it would kind of like fill it and so on and so forth, go round and round. I think I had some sort of issue anyway, which made me decide to go this way with actually explicitly defining it by determining that there is definitely a sample in that final sample index before incrementing the value. So we're actually going to do else if, rather than just else and letting it kind of increment through all of those sample values. Else if final sample val is not equal to 0, so in other words it is storing a value currently, we're going to do transmat size incremented by 1, so plus equals 1, and then we're going to post this to the max console as well so we know what's going on. We'll post just use that prefix again. We will post something like all indices full, and then we'll do transmat size increased by 1, and we'll close that up, and we'll post what are we looking for here? We'll just post the new transmat size. So we'll do transmat size equals transmat size. So we have a reference for what's going on there. And then we're going to output the new transmat size. We're going to do out3 equals transmat size, and that is what we're going to connect up to this here. So we'll do out3 equals transmat size, and we should hopefully get a new output. Maybe we won't just yet because I've not defined. Is there anything there? No, I think I need to define output 1 and output 2 first. We need the bracket for that as well. Close that off. That not resolved it. Oh, that is a curly bracket. Okay. So this was a curly bracket which was causing us our issue. So we can do this again. Okay, so that's now fine. But we're not going to get that out 3 just yet. We need to just change that to maybe out 1. So undo that. No, that's fine. So that's our out 3. So we connect that up there. So we're changing our size. Okay. So we also actually need to write our sample val, our current note, to our new sample index. So we output that and we change the transition matrix size out here. The reason I've done it this way is I don't think it's possible to change the dimensions of a buffer inside Codebox or a data operator. I could be wrong. maybe that's because this data operator is referencing this data operator, so you have to change it outside. I'm not sure, but this is the way that I managed to get it working. I couldn't get it to work with changing the dimensions of the data operator inside Codebox itself. So we will continue on. So we actually need to poke this value in, so we're going to do poke, and we're going to do transmat. Again, we're going to poke the current note variable into transmat size -1, and we are going to do this at channel, the current channel. So we can close that, and then we can post again, just as a frame of reference. So we can see everything that's going on here. Wrong thing. There we go. And then we want sample. We want new sample. Is this the same thing as before? I think it is. New sample val stored. It's exactly the same thing as before, so we'll just copy that. New sample val stored at we've got new sample val stored at channel chan sample equals current note, and we're done. So then we can break that at that point, and just down here below, outside of this if-else statement, the else if statement, we are also going to post gtm, no, wrong name. I'm going to post my Markov chain, sample val at index sample equals sample val. So we'll see how this all kind of prints to the Max console shortly. And then, so this is everything that happens if the preceding two notes are equal to one of the note pairs already stored in the transition matrix. If there is not a matching note pair already stored in the transition matrix, then we need to store the current note pair, which is our preceding two notes variable, at sample index 0 of the next sequential channel inside the transmat data operator, and then store the current note, which is our third note of our incoming 3 note list, at sample index 1 in the same channel. So for this, we've got post, and then we can break that as well at that stage. So we'll do break, and then that takes us out of this if statement, or out of this for loop. It takes us out of this for loop, and it breaks the if statement at this stage. Otherwise, we want to do else if again, sample 0 is equal to 0, so empty. We're going to post first of all, just as a reference, and we're going to do my Markov chain colon, and we're going to do no match So then we're going to again, we need that. We're going to again do poke. And we're going to use the poke operator, and this time we're going to do transmat again, and we're going to poke the preceding 2 notes this time into sample 0 at the current channel and close that up, and then we will post again purely for reference we will do new note pair start at channel chan equals chan will do, sorry, index 0, just to make that extra clear, equals, and then we'll do preceding 2 notes, just like that. Very good. And then we need to store our current note. We've just stored our preceding 2 notes, or our note pair, in sample index 0 of the current channel. We need to store our current notes, so the 3rd note of our 3-note list, into sample index 1 of the current channel. So we do poke again, and we do transmat again. And this time we do current note at sample index 1 of the current channel, close that up, and we'll post that to the Max console as well, so we can see this all happening. And refer back my Markov chain. We want to do new sample val stored at channel chan wrong thing, sorry, index 1 equals, what's happened there, channel, go, chan index 1 equals current note, just like that. Very good. And then we need to increment our active chans param by 1 before we can close everything up and we finish this off. This compileMatrix function, so we need to do active chans, because obviously we have 128 channels, but we only really want to be looping around when we're recalling generating note values. We only really want to be looping around with for loops the number of channels that are actually in use, rather than potentially looping higher than that. So we just do active channels plus equal 1, and then we will post that as well. For reference, we'll do this again as prefix, and we'll do active chans equal active chans. Very good. And then we can break that there. And then finally, whilst we're doing this, just for additional reference, outside of this, we've got else if, that needs curly brackets. Outside of this for loop, but inside the function, we want to be outputting our preceding 2 notes and our current note. So just like this. Out 1 we will do equals preceding 2 notes, and out 2 can equal our current note. So at every loop we should see the preceding 2 notes come out of here, the current note come out of another outlet out here, and then this, the transmat size, will come out of the 3rd outlet. hopefully this is all fine. Seems to be. So this we want to connect up now to output 3, and here we can comment some stuff out. This is going to be our current note. We're actually going to use that to generate our bang at the very end of compiling the transition matrix. And we will just comment this stuff out so we can see it. Current note can just go there. We are not yet outputting active chans, but we will be doing that at the end. So this is fine. Okay, so I think that is all okay. We just need an integer box here, and we just need a comment saying proceeding to notes. We can resize that, and then let's have a look and see if this works. So we can come out, we can come into here, we can connect this up. So here we've got our list. Here we've got bang for next note, which we're going to have connected up to that ultimately. Although we're not going to turn the transport on yet, that will be bang to reset. Here will actually be the note output, which we don't have yet. This will be bang when complete. That will be nothing. We can put that, connect that up to there, and then we can go back. We can open up this. Hopefully we're seeing our list. We're not seeing anything happening in here for some reason. Oh yeah, we are not calling the function. We need to do compile matrix list in 1. We call the function there. That should now work. So here we can see that we have compiled our transition matrix. If we just pick out something at random, we're iterating through and it's telling us what sample 0 is, channel 0, 1, 2, 3, 4. We don't have a match here, so we are oh no, we do have a match. Sample val at index 1 equals 51. New sample val stored at channel index at channel 8 index 2 is then 56. If we find an instance where we have no match up here, we iterate through all the channels, we get no match, so we do new note pair stored at channel 15 index 0 equals this. This is our encoded note pair, and then we do new sample file stored at channel 15 index 1 equals, where's that gone? Channel 15 index 1 equals 58. And then we do active chans equals 0. That's not right. Active chans, it's always equaling 0, so there's something wrong there. Active chans plus equal 1. That should, that's not an equal sign, is it? That's why I've done plus minus 1. There we go. If we come back here, we compile this and we find another thing where there has been no match. here we can see an example where all indices are full, transmat size increased by 1, transmat size equals 11, transmat size will previously have been 10, new sample val stored at channel 6, index 1 is 54. Matching pair found, increased by 1. Okay, so we don't have any matching pairs up until that point. So that's why up until that point. Sample val stored at channel 6. Yeah. New sample val stored at channel 6, index 1. No, that doesn't sound right. Let's just do poke transmat, and we'll do, sorry, peak transmat. I'll just connect up 2 number boxes. I think it's just the way that we're porting it using that sample value. I don't think it's actually the way that we're writing it, in which case it's not a problem, but we'll just double check. All indices full. So here we've got channel 6, index 1 equals 59. Yeah, we're writing it fine. We're just reporting it incorrectly. So if we go down to channel 6, index 1 is 56, but index 9 should be 59. Yeah. So we are writing it correctly. We are just reporting it incorrectly. Okay, so all we need to do here then is change this, all indices full, change that to that. Oh, after unlocking it, should give us what we're after. Let's have a look. All indices full, transmat size was 10, channel 4 index 9 equals 54. Good. Okay, so good. Okay, the next thing to do is to create a notePairCheck function so that we can check when we want to generate something. We can check our last 2 notes against all of the note pairs that are in the transition matrix already. So we're going to do that after we've called compileMatrix here. So we're just going to call this function notePairCheck, and it's going to take a note pair, and in here we're going to have another for loop. So we're going to do for, we're going to use variable chan, which is going to be an int. We're going to let that equal to 0. And as long as our chan is less than the active chans, we're going to do chan less than active chans. Oh, no space. We're going to do chan plus plus. Good. Okay, and then we're going to do this, make a bit of space. Okay, so we need some more variables. Now we can use the same kind of variable names as we've used before, because they are their scope is limited to the kind of function in which they exist, so that's fine. And it just kind of makes it easier. It gives you, or at least I think it does, you can give these different names if you like, but it can get pretty complicated pretty quickly if you do that, and it just makes it easier if you've got kind of like corresponding variables in different function calls and things like that, that essentially mean the same thing. So we're going to have another sample 0 here. We're going to do let sample 0. This is again going to be an int, and we're going to make that equal to the output of a peak operator looking at transmat sample 0. We need to define the number of channels, which will be channels 1 to 8, as we know, and we're going to be looking at the value of sample index 0 in all channels in the transition matrix, all active channels in the transition matrix, until we find a corresponding value, or not, as we may not find a corresponding value, in which case we think we'll do kind of like random generation. We'll choose a random note instead. So chan plus, we've got that, and yeah, sample 0 is equal to the note pair, essentially, in the sample index 0 of every channel, every active channel in our transmat data operator or object. So here we want to do, oh, what have I done? That function needs an end. Okay, so we want to do an if-else statement, or an if-else-if statement. So we're going to do if sample 0 is equal to our note pair, which is this. I'm just going to give that a capital P. Sample 0 is equal to our note pair, then we are going to return the channel number, like that. Otherwise, else if chan is equal to active chans minus 1, so essentially it's reached kind of like the maximum limit of the active channels. We're going to post essentially there's not going to be a match, so we're going to choose a random channel. So we're going to do no matching note pair random chan chosen. That's good. And then we're going to return a value, which will be a random value, which we'll assign to our channel, the random round, so the round operator, and we will do random between 0 and, because this will generate a random floating point number, so we're just going to round it to an integer, active chans between 0 and active chans minus 1, close that off, will give us a random channel number because we've generated a note pair that doesn't match a note pair inside our transition matrix, which could lead us to being stuck. So this should hopefully cause generation to continue on without needing any manual intervention from us. So that's fairly straightforward. That is our notePairCheck function. The next thing we need to do is we need to check the sample value, which is a function to check the number of notes that are associated with a note pair, a given note pair, the note pair that is determined by our notePairCheck function, in order to kind of like do a for loop for that length of time, or sorry, not a for loop for that length of time. We do a for loop to determine how many samples are stored against that note pair, and then we use that as the upper limit of another random kind of function to generate a random number within that range and choose a random note associated with a given note pair. So with our sampCheck, we need to create a new function down here. We're going to do function, and we'll call this sampCheck, and this will take a channel. This will take a channel, chan, and then we're going to do this, close that off, and here we're going to do another for loop. So we're going to do for let sample, which is going to be an int again, equal 1, because we don't need to loop through the sample index 0 where our note pair is, as long as sample is less than the dimensions of our transmat data operator. We're going to do sample ++ and increment that value, and then down here we're going to do define a sample val variable, let sample val, which is going to be an int, equal peak. It's going to be the value of peak transmat at sample index sample, number of channels 1 to 8, chan. So this is our sample value at the current sample index of the of this kind of like iteration of the for loop in the current channel, in the channel number that is fed into the sampCheck function as its argument, and we get this channel number from our notePairCheck function. In order to get the sample value that we want, and so what we do here is we close that off, and then we do an if statement. Oh, this for loop needs to be closed off. We're going to do if sample val is equal to 0, then we're going to return sample -1. So essentially, if we have a note pair in a channel that has a number of notes assigned to that in indices 1 and up, but it does not fill all of the sample indices as determined by the dimension size of the transmat data object, which means that there is essentially another note pair in another channel that has more notes associated with that note pair, then we just kind of iterate through the for loop until we find a 0, and then we return the sample value. We return the sample value of 1 less than the sample that we're currently at, and then that gives us our number for our upper limit for our random kind of value generation to randomly choose a note associated with the note pair that we found. So we return sample -1. Otherwise, else if sample is equal to the maximum dimension equal to transmat minus dimensions of transmat -1, then we return the dimensions of transmat -1. It's like that. Return like that. Okay. Okay. So that is our sampCheck function. And then finally, we need to create a function to actually string these things together when we bang a note. We send a bang into the object, what is going to be our external object, in order to generate a new note. So what we need to do here, and we're actually going to need to make another couple of functions for decoding the notes, so getting the first note, getting the second note, in order to extract them from our encoded note pair and then build the next note pair, and so on and so forth. And those functions will be called within this next function. So this is going to be just a bang function that is called when a bang is received into. So we're going to put this at the bottom here, and we're going to do function into bang like this, and close that off. And then we need some empty placeholder variables. So we're going to do let chan is going to be an int. We're going to do let sample count is going to be an int, and here we're going to do let sample is also going to be an int, and let last note is going to be an int. And then we need another if-else statement. So here we're going to basically, if note out, so our note out param up here, which is set to 0 when we input a new list, and starts at 0, if that is equal to 0, then we need to randomly choose a channel, and then randomly choose a sample associated, or a sample index or associated note in that channel. Otherwise, if note out is not equal to 0, then that means that a valid note has been generated in the previous call to Codebox. And so we do something a little bit different. So what we're going to do here is, in the instance where we're either kind of starting off for the first time, or we've pressed our manual reset button in the max patch outside, we are going to do chan equals, we're going to use a round operator, random, again between 0 and active chans -1. So this gives us a random channel, basically, which is fairly straightforward. And then we will post that to the Max console so we can see that it's working correctly. We'll take this and we will do chan equals chan, like that. And then sample count is our other variable that is going to be assigned to the output of our sampCheck function. into which we're going to feed our chan variable, which we've just determined randomly up here. We've generated a random channel. Now we're sending that random channel into our sampCheck function to determine how many notes are associated with that note pair in that channel. So we just do that, and then we do post, same thing again. And this is just going to be sample count equals sample count. Very good. So here we need to assign we need to create some new variables. We need to create a new variable for the first two notes, which are basically going to be the first two notes that we don't actually kind of hear. So it's basically like the first two notes in the channel. Yeah. So we don't hear them, but they're the first two notes in the channel, and we need them to create our next note pair in order to generate the next note. So we'll take the second one of those two notes from our first two notes, which is our note pair in this channel, and combine that with the note that we randomly generated associated with that note pair to create our next note pair, which is then used for the generation of our next note. So we need to create a new variable, which will be let first two notes, which will be an integer, equal peak transmat sample 0, define the number of channels with 1 to 8 at chan, again using our chan variable here. So that's our first two notes, and then we're going to post this again. So we're going to do something similar to this, but change some of the details. We'll do post first two notes, encoded is equal to first two notes. Good. We need that close parentheses there. Good. So we've got our first two notes, and then we need to create a function to get our second note. So essentially we will call that function here. We'll call it getSecond. In fact, no, we'll write the function first. So we're going to go back up to the top, and we're going to write a function called getSecond, which is a function for getting our second note. We're also going to write a function called getFirst, but we're not going to write that just yet. To get our first note from our encoded note pair. So function getFirst, and that will take an encoded note pair, and that's going to go here, and then we will do function getSecond, and this is also going to take an encoded note pair, and we will do this. So in order to get our second note, what we need to do is we need to create a new variable in here, and we're going to do let second note, which is obviously going to be an integer again, equal encoded note pair minus the output of our getFirst note function, which I will write in a second. In fact, I'll write that now. Let's just comment that out, just so we don't produce any errors along the way. So to get our first note, we're going to do let first note. This is a variable, obviously. Let first note, it's going to be an integer equal encoded note pair bit shifted to the right by 8. So shifting 8 bits to the right, this is equivalent to dividing by 256. However, if we do divide by 256, it's also necessary to use a truncate or floor, so trunc or floor operator on the output of that, but as bit shifting works only with integers and doesn't return floating point values, we don't need to actually truncate this value. I think that's correct. If we were doing it just by dividing it by 256, we would need to either do trunc or floor on the output, because the value that's returned would be a floating point value. But bit shifting should only return an integer, I believe. If I'm wrong and you know better, please feel free to tell me so in the comments, and I can update the code in this external object. But essentially, we're just bit shifting to the right. It knocks off the kind of floating point value that is left over, which is the value of that is determined by the value of our second note in the note pair. So we just end up with our first note in the note pair. So we bit shift by 8 steps to the right, equivalent of dividing by 256, and truncating the output. And then we will post that so we can see what's going on. So we'll do post. Let's get this again. And that is going to be first encoded note equals, we'll close that off and we'll put in first note, and then we just return first note. Yeah, so we've got our function to get our first note. To get our second note, we need to have our get first function to call in here. So to get our second note, what we're doing is we're declaring this variable let second note. It's going to be an integer equal to the encoded note pair minus get first, the result of the get first function into which we feed encoded note pair, again bit shifted by 8 bits to the left rather than to right. So here what we're doing is we're shifting it by 8 bits to the left, which is equivalent to multiplying it by 256. So this is giving us an integer value again for our second note, which is essentially the bit that is truncated off this point. And we just do this. So then we do post again, and we just copy this in. We'll just take that whole thing and paste that into there, but we'll do second encoded note equals second note, and then we return second note. Very good. So that's how we decode our two notes from our encoded note pair. Good. So here we're bit shifting to the left to encode them, bit shifting back to the right to get our first note, and then doing our encoded note pair minus the first note, and then bit shifted 8 bits to the left to get our second note. That's very good. So we can come back down here. Hopefully this all should work. We can come back down here to our into bang function, and we've got our first two notes here. So our last note is where we call our get second function. So we go last note, we've declared this variable up here already, equals, here we're assigning a value to it, last note equals get second, so we're calling that get second function into which we feed the first two notes, which we've just assigned a value to up here. So last note equals get second, first two notes. That gives us the last note there that we're going to use to create our next note pair, and we're going to post this again like this, and we're going to do last note equals last note. Good. And then to get our actual sample value, we're going to do sample, which we've again declared up here but without a value assigned to it, equals round random 1 with the sample count, which we've determined the sample count via the sampCheck function here. That's the upper limit. So this is the random note value that we get associated with the note pair. Associated with the note pair that we've got out of our first two notes here. So we get a random sample value, and then we assign that to note out. So we do note out equals peak, and we do inside transmat, as we have been doing, that's our only data operator, at sample index sample. We define the channel count. Channels is 1 to 8, and we do it at where are we at? We do it at channel chan, and then that gives us our note output, which is a random note value associated with a random note pair, because remember we didn't have a note pair to begin with, or we didn't have a note output to begin with. So this is like starting from the very beginning when we don't have a preceding note pair to work with, or when we manually reset it. Chan, and then we need to create a note pair for use in the next kind of generation round. So what we do is we update the last two notes param value here by encoding a new note pair into which we send last note, which is the second note in our preceding note pair, which is our kind of like note pair associated with the randomly generated channel from up here. Encode last note and note out, and that gives us a new note pair associated with last two notes. So that's what happens if we're at the very beginning and there is no value, so 0 is assigned to the note out param, or if we press this manual reset button here, which resets the note out value to 0. Here, otherwise, if there is a number associated with note out, we're going to do this. So else, we're going to do into bang. Where have I created? I've not actually created an if statement, have I? That was a mistake. So what we need to do is we need to go if note out. Oh no, that happens further down. We need to do that under here. So we're going to do if note out equal to 0. Then we're going to do a function. We're going to shift all of this along. Else, if we have had kind of like note previously generated, so we're not starting from the start and there has been a previously generated note, we're going to do chan. In fact, before we do that, let's close that off and also close that off. So else, we're going to do chan equals, we're going to do note pair check, so call our notePairCheck function, and we're going to apply that to last two notes in order to return either, if we come back up and look at our notePairCheck function, which is, where is it? Where did I put that? notePairCheck. it's either going to return the channel number associated with the current note pair, or a random channel number, which we get down here, if there is no corresponding note pair to the note pair that we've just generated through the second note of our preceding note pair and our currently generated note. So we're going to do that, use that notePairCheck to get our channel value, and we will post that. I think we can just copy this over from here. Yep, so we then need to do sample count, and we just do the same thing again. So this should be sample count is we're doing the sampCheck function, into which we're sending the chan as our argument, and then we are posting that to the max console again, and then we need to get so here we had to get or create a first two notes variable because we didn't have a note pair, a preceding note pair to work with. So we had to do let first two notes equal peak, and then look at our randomly look at the note pair associated with our randomly generated channel number to assign that to our first two notes. Here we can just look at the last two notes param, which holds our note pair from the kind of preceding call to the second order Markov chain object or function or series of functions that's taking place inside Codebox. So what we'll do is we will just do, so here we did this, here we're just going to do last two notes, that should actually be capital, encoded equals last two notes, and then to get our last note we need to do the same thing again basically, but on our last two notes rather than our first two notes. So we do get second on our last two notes, so the same thing as above, we call our get second function, which calls our get first function to get our second number of our encoded note pair, and we apply that to our last two notes param, which we feed into the get second function as its argument. So we do last note equals get second last two notes, post that to the max console, then sample, we again randomly choose a sample index associated with our note pair. So we do round of random between 1 and the sample count, because we can ignore the first sample index where a note pair is stored, and that's the sample count for the current channel. And then we need to do note out is going to be peak transmat at sample at channel, so our randomly generated sample at the channel of our last note pair or a randomly generated channel. We actually want to post what's happening here, which I didn't do last time, but we can we can copy it up to the other bit as well. Post, we're going to do GTM, we're going to do my_Markov _chain, and we're going to do note out equals, close that off and do note out, and then we're going to do that. And we will copy that up to there. Good. And then down here, we're going to do, we need to encode another note pair. So it's the same thing. Last two notes, encode, last note, and note out. So that is everything. I just want to create another couple of outputs, which are going to be out 4 is going to be our active chans, so we can monitor that, our active chans param. Out 5 is going to be our last 2 notes, and out 6 is going to be our note output, note out. So that is everything. That's it all done. We just need to connect some things up. So out 4 should be active chans, which we need to just tidy up some of this stuff. Let's drag that, leave that around about there, and shove that up to there. That's fine. Drag this over to here. These are all fine. Then here we want an integer box so we can monitor it in here. So this is out 4, which is our active chans. This is out 3, which is where we output our transmat size further up in the code. Out of here, we're just going to have another output. So we're going to do out 3 for this, at comment, and this is going to be active channels, and then we're going to just stick that there, resize. Then this is actually going to be our next note pair, even though we're referring to it as last 2 notes because it is our last 2 notes param. It's actually the note pair that will be fed back into the algorithm to generate the next note. So it's not like the last note pair, it's the next note pair, and we will comment that appropriately so we know what's going on. So we stick active chans in there. And then over here we want essentially the same thing, but just to change the words. So that's going to be out, that's actually going to be out 2. It's going to be our next note pair. And then we'll do next note pair. Good. And then here we get our note output. So out 1 is our note output, out 2 is our next note pair, out 3 is our active channel. So this is just for like monitoring purposes. And then out 4 is our bang when everything is done. And this should work. We just need to connect into up to that. Oh, error. Is that an error? Okay. To do with the get second or get first functions. Is that? There we go. Okay, so that essentially should be everything now. So let's check if it works. Let's save it, close that window, connect this up. Next note pair. Active chans, we don't use that for anything, we can move these along. compile our matrix. Seems to be fine. And let's try some audio. Oh. Let's give it a go. And we can try changing the scale. I have a few snapshots for this. Change the octave. And that works fine. Brilliant. So, if we have a look at this, we're kind of like feeding out every time we generate a new note, which is what we want. We won't see this when we're actually using the external, but we can now export that external. If we stop the transport there, we come back into here. Here we go. Max external export. We'll do both, so we can see where that's being stored. We can do that in there. I'm going to give it my name. An external for second order Markov chains is fine. Tags, we'll call it we'll say Markov chain, algorithmic, generative. That's fine. We don't need to include transport attribute. We don't need an MC wrapper. We can disable polyphony. Don't need to expose voice params. We may as well open export directory, and then I will hit export. Okay, so we're back, and it has exported both our Windows and our Mac's externals for us. I'll just minimize that. We can get rid of this. We're going to save this, and I should just be able to create an object called my underscore Markov underscore chain. There we go. And what I'll do is I'll copy. Yeah, I'll just cut that out so we can keep this in the patch and slot this in here. So I'm going to go like this. This, 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 this. Oh. There we go. Stretch that out a bit. Good. Now you will see that we no longer get things printed to the Mac's console, but everything should work as we want it to. So here we've generated a 32 note list using Uzi and then Drunk, and quantized that to a specific key signature, and that has been sent into the myMarkov chain external object. So, hopefully, I've managed to successfully convey some of the information I've been trying to in this video, and you've learned something useful. As I said at the beginning, this is available to download. You should be able to find it in the information below the YouTube video. I'll post a link to download the patch and the project and the external object down there. And yeah, hopefully you've enjoyed this and it's been in some way fruitful. We can reset this. There we go. It's been in some way fruitful, and you've learned a few things about RNBO and Codebox in RNBO along the way. That's it. My name's George Meikle. Thanks very much. Yeah, enjoy it.